Morning, everyone, and welcome to the JKMRC Friday Seminar Series 2026. On behalf of the University of Queensland and the Sustainable Minerals Institute, we would like to acknowledge the traditional owners and custodians of the lands on which we meet today. We pay our respect to their ancestors and their descendants who continue cultural and spiritual connection with country, and we recognize their value contribution to Australian and global society. So it's my great pleasure to welcome Andrew Langendam. In a past life, Andrew was a planetary geologist interested in element mobility in the early solar system. Specifically, he investigated how increasing ice content can affect the structure and composition of a resulting planetary body. He also has led field expeditions to search for meteorites fall throughout Australian desert. Since joining the synchrotron, his work has focused on developing and refining data collection for geoscience at the X-ray fluorescence microscope, or the XFM beamline, including developing a technique for rapid collection of collocated fluorescence and microdiffraction maps. So today his talk will be about the XFM beamline and multimodal geoscope. Please join me and welcome Andrew. Thank you, Andrew.
Thank you very much, Olivia. Yes, I am Andrew Langendam, down at the synchrotron in Clayton at the moment. Thank you very much for allowing me to give this talk, where I'm going to go through a bit about my beamline, but also more generally a little bit about the synchrotron. But in the grand scheme, I'm trying to focus on this idea of multimodal data collection at a beamline or at a single facility. So just see if I can, yep, there we go. So the contents of my talk, I'll give you a very brief introduction to synchrotron radiation and a bit of an introduction to the XFM beamline, in which I will include a little bit about X-ray fluorescence for those of you who may not necessarily be fully comfortable with it. In some of my slides, I do apologize. I am giving a talk to a geoscience community or geoscience audience. I have got a couple of little bits of maths in there. I hope it doesn't scare anyone away. But then I'll go into the chemical mapping that we mostly do here at XFM, and then I'll get into some of our correlated techniques. And you can see them listed here, but I'll go into detail into what all of those mean. So just for a bit of context, ANSTO is the global organization that the synchrotron is part of. We have two campuses. One is our main campus is up at Lucas Heights in New South Wales. That's where we have the Opal Research Reactor, which produces a lot of the medical isotopes for Australia, plus a lot of neutron scattering and particle physics facilities up there. So if you need to do anything like that, you can go up to Lucas Heights, but we are down in Clayton at our secondary campus, which hosts the Australian Synchrotron and National Centre for Synchrotron Science as well. We are on Bunurong country here down in Clayton and Dharawal country at Lucas Heights. So here's what the facility looks like from an aerial view. We've got a lot of buildings around. We've got a couple of beamlines that extend out, have very long optics, and that's required for the collections that they're trying to do there. So the IMBL is our longest beamline. Nanoprobe is a close second, and that's going to be commissioned hopefully in the next year. You'll also notice we have a lot of solar panels on our roof. We produce about 30% of our power through these solar panels. So we've got this lovely thing of we study solar panels. So we use solar panels to make light that studies solar panels to make them better, which is great. So how does it all work? So at synchrotrons, you essentially have normally three kinds of accelerators. You have, first of all, everything starts out with an electron gun. You need to source electrons from somewhere. So this is very much like an SEM or a cathode ray tube. This produces a lot of electrons. They then get accelerated through a linear accelerator. And at the Australian Synchrotron, this is about a 20-meter long linear accelerator that accelerates the electrons from about 60% the speed of light up to 99% the speed of light. Then those go through what our first synchrotron is, which is the number 3 here, our booster ring. This accelerates the electrons from 99% the speed of light, where they're going pretty fast, but not fast enough, to 99.9999985% the speed of light, where they're relativistic. And this is when we start to get emissions from the electrons, which are in the X-ray wavelengths. Those electrons then get injected into our storage ring, where we have all of our beamlines coming off. So part of this is, well, why would you come to a synchrotron in the first place? Well, it says here, synchrotrons are really, really bright. They're a trillion times brighter than most lab sources. They're a million times brighter than the sun, at least. So there's not really another option to get as bright a light as we can produce here. How do we do that? Well, charged particles, when they oscillate, will produce electromagnetic radiation. So this will normally expand out in a ring from the particle, and as that particle from what we call the electron frame of reference, everything is expanding out in a ring. But if that electron is then moving very, very fast, every time it emits some radiation, that radiation gets bunched up. And here's our first bit of math, which I'm not even going to talk about, but basically this means that you bunch up blue shift or Doppler shift all of those wavelengths up to very, very high energies when the particles are going very, very fast. To get the light out, you need to induce a force or induce an acceleration on the particles. Essentially, in our case, that means we put them through a magnetic field and we turn them. So there's a number of ways we can do that. The first thing we need to do to get everything in a synchrotron around into a ring is we need to have a whole bunch of what we call bending magnets. These are magnets that have a single magnetic field being produced. It's normally reasonably strong, and it bends our electron beam through an arc, and all along that arc, our electrons are emitting light. You can then use that light for whatever you want to use it for. Then there's these other things called wigglers. These are a different kind of insertion device, what we call insertion devices, which are how we start a beamline. And these are essentially if you've stacked up a whole bunch of bend magnets together. This essentially is able to then produce light every time you turn the electrons. You wiggle them back and forward, and every time they turn around, they produce a cone of light. And then XFM has a different kind of insertion device, which is called an undulator. And this is very, very similar to a wiggler, where you've got these opposite poled magnets in periods. But the idea is to restrict the movement of the electron beam so that when you're looking down all of your pipes and trying to look at your source of X-rays, that all of the wiggles and wobbles stay within the visible distance of that particular insertion device. So all these different insertion devices produce different kinds of radiation. Bend magnets produce very bright light that's over a very broad range. Wigglers, which are essentially bend magnets but more, produce more intense light and normally higher energy light, and it's dependent on the number of periods you have within your wiggler, so you can produce very, very bright light with a wiggler. And then for an undulator, because everything is controlled for within our visible angle, what we call a solid angle of our source, you can get your emitted light interfering with each other. You'll get constructive and destructive interference, and so you end up with harmonic light. This is very, very good because you can produce very, very bright light in very controlled energies. So XFM has an undulator because we want to be able to set our energy very accurately to be able to then do all the techniques that we want to do. If you want to think about these as normal light sources like we have around everywhere, you can think of a bending magnet sort of like a standard downlight, a wiggler more like a big floodlight or a stadium light, and then an undulator more akin to sort of like a laser pointer where you can select the color of laser. So how does it all work? Well, we've got this storage ring, which is producing all of the lights. We have an insertion device in there. It's sending out a whole bunch of X-rays. These then come down through a whole bunch of vacuum tubes and into some optics. They might be focused by those optics. They might be conditioned by the optics. We might use the optics to collimate the beam. We might use the optics to set an even more accurate color to the beam. And then, so that all happens before everything gets into our, what we call our end station, which is where the action happens. That's where you can put your samples, you can have the X-rays interacting with your samples, and you can do a whole bunch of different science. So here's just a little bit of what the Australian Synchrotron produces. So we're much brighter than most other sources. And we also have this very broad range of light that's available to us. We go from microwaves all the way up to gamma rays, and we can use all of those for different purposes. In fact, we've got a whole bunch of different beamlines. We've got beamlines that are focused on crystallography. We've got beamlines that are using the infrared produced by our synchrotron. We've got imaging beamlines. We've got spectroscopy beamlines. There's a lot of different techniques you can do here. But for today, I'm just going to be talking about XFM, although I will be touching on a lot of these different techniques. So just so we are all on the same page about fluorescence, X-ray fluorescence. If you want to understand a sample, especially the chemistry of a sample, it's very good to map it in high resolution. So to do that, if you expose it to X-rays, those X-rays, if they're of the right energy or the right color, they will eject an electron from a core orbital within the electron cloud. That ejected electron then leaves a hole, and another electron in a higher orbital will fall down into that hole, and it will emit a photon. That photon, the energy of that photon, is controlled by mostly the number of protons within the nucleus of that atom, but I'll also mention that it is also controlled a little bit by the oxidation state of your, or the ionic charge of your atom, and what else is bonded to your atom as well. So this means that when you then look at your spectra, that is, or the light that comes off your sample as a result of exposing it to X-rays, you'll get these peaks that all correlate to different elements. And if you solve for those peaks, if you do some complicated maths and solve for those peaks, you can work out how much of each element is contributing to this overall spectrum that you're getting from your sample. And this means you can select a particular element and have a map just of that. This is a rice grain. This was a study that was looking at increasing nutrient content within rice by the Grain Research and Development Corporation. And yeah, they did some very good work, and they regularly come here. Some more figures and maths. Our beamline looks a bit like this. We start with this undulator. Our beam comes through out of the storage room wall. It then gets conditioned by some optics. We've got a number of different optics here. We reject harmonics and focus the mirror in our horizontal direction. We then set a color to it with either our dual crystal monochromator, or DCM, or our dual multi-layer monochromator, our DMM. And then it goes through some other slits and things to eventually get focused down to a 2-micron spot, 35.5 meters from our undulator. So this 2-micron spot means that we can then scan a sample back and forth in that beam, and then we can build up these maps. Here's just some photon flux measurements for our beamline. This paper here, this XFM beamline paper, is pretty up to date. We've only had 1 or 2 upgrades since this paper was put out. So if you want some more information on the workings of the beamline, please go ahead and go to that particular paper. The only addition, the major addition, I won't say the only addition, but the major addition since this paper was put out is now we have, rather than space for a DMM, we have a DMM. And that is producing 10 to 20 times as much light as the DCM, but there are some caveats to what you can do with that light. So fluorescence microscopy, our energy range, we go from 4 kilo electron volts all the way up to 30 kilo electron volts as an incident energy for mapping. So we are a hard X-ray microprobe. With our DCM, we have this funny figure called delta E over E, which is basically our energy resolution. That means for a 10 kiloelectron volt beam, we have for the DCM, the spread of that beam, the full width half maximum of that beam is only 1 EV wide. For the DMM, it's about 100 EV wide, and I'll get into why that's important later. So we do a whole bunch of fluorescence mapping. We do XANES imaging. We can do fluorescence tomography, although I'm not going to talk about that today. The applications of fluorescence tomography, because you need a very, very light sample, a very light matrix sample, very low Z. It's not really applicable for geosciences, unfortunately. But then we do some of these other techniques as well. This X-ray scanning diffraction microscopy. We do Ptychography, microdiffraction, all this sort of stuff. And we have two main end stations as well. We have a microprobe and a milliprobe. We have a number of different detectors as well. We've got two Maya 384 silicon diode detectors, one for our milliprobe and one for our microprobe. We have a single element silicon drift detector, one of these Vortex EM detectors. This is kind of a bit of a backup detector for us at the moment. It's not actually on the beamline, but we have it available if you need it. We also have now a 3-element silicon drift detector that's been in operation for about 5 years. The advantage of that over the Maya detector is you get better energy resolution. We also have an Eiger imaging detector, and we're in the process of commissioning. I think I've been talking about this germanium detector for probably about 3 or 4 years. It is still coming soon, TM, hence the TM. We just can't mount it on our stages at the moment, but hopefully soon we'll be able to do that. So why is all this important? Well, geology at XFM, I don't think I need to really say too strongly to this audience that mining and minerals are a key industry within Australia. For XFM, a large chunk of our user base is in earth and environmental sciences. So that's people who are looking at structural geology, people who are looking at ore deposit geology, people who are looking at mine waste and remediation questions, people who are looking at things like mangrove swamp, mud oxidation, or how mangroves can introduce oxygen into sediments. A whole wide range of different things. In fact, earlier this week, we had some people come over from New Zealand with some large speleothems, so some large stalagmites, to try and track fault and earthquake records in those speleothems as well. Don't quite understand how they were going to do that, but they assured me that they were able to do it. But one of the big things about any geology or any environmental science is you're normally sampling over large areas, or you need lots of context for your question to be answered properly. Here, I've just got a bit of an image from one of my meteorite expeditions where we were covering hundreds of kilometers of walk distance, where meteorites were spread out over these hundreds and tens to hundreds of kilometers, and trying to relate those meteorites to each other to see if they came from the same fall can be quite difficult. So you need to map things at large with large maps. And this comes to the question of resolution versus definition. We always like to not necessarily talk about resolution, because resolution is only so good. It essentially means this is the smallest feature size I can look at, whereas definition gives you that context. XFM is being built for context. So we can get down to 1 micron or half micron pixels. We can sort of do 20 nanometer pixels if we really want to, but that's never really used. I wouldn't really recommend doing that. But the advantage of XFM is we can map 1 micron pixels across a very large area relatively, 140 millimeters by 100 millimeters. So this means that you can scan a very large area and get very good context for your project. The milliprobe is a lower resolution instrument. It can only get to 50 micron resolution, but it can map a much larger area, so 600 by 1200 millimeters. And so this essentially means that the only limit you have when you bring samples to us is time to get your chemical information. We often do gigapixel images, and if you wanted to map the entire scannable area of our microprobe, It'll be a very large image, 35 terapixels, which if you really wanted to display it all at once, you'd need 4 million 4K screens, which is quite a few. So here's sort of what this looks like. Again, I'm a planetary scientist, so I've got some meteorites for you. Normally, we're scanning things that are more than 10 millimeters by 10 millimeters. These thin sections are on 25 by 45 millimeter slides, and I can map the whole thing in relatively short amounts of time. These maps here, these are 20 micron maps, and they took about an hour to collect. So very low collection times. But in this, I can now see from my what looks like a sort of muddy gray and brown rock, I can see that there's an accumulation of calcium in the middle of this rock. There's iron hasn't seemingly been affected much, and there's some manganese on the outside. Great. What does this mean? Well, from previous studies, I know that meteorites, when they weather, like to wick up water, and given this was found on the Nullarbor is a karst system, so there's probably going to be a lot of calcium deposited in the center of this meteorite before it starts breaking up. So we can do this. We're very sensitive to low concentrations of elements across these large areas. And really, this was developed for the last 16 years with the help of the Maya detectors. These are very, very fast mapping detectors and are designed to find those instances where you have a very small grain of something in a large sample, but you want to find the small grain. If you had like a grain of gold in something the size of the MCG or the GABA, we can find that, essentially. So let's talk about a bit of a case study here. For some high-resolution mapping, this is a project I've been involved with some collaborators over at the University of Auckland. They are looking at samples that are similar to some things that were found by the Spirit rover in Gustav Crater on Mars. So this is what we think is a volcanic or a hydrothermal sinter deposit or silica deposit. It's got these digitate-like structures, these finger-like structures that have been formed that are very similar to these finger-like structures we find in hydrothermal systems on Earth. The great thing about the stuff on Earth is that every time you find these, they are mostly inhabited by extremophile microbes, so archaea and bacteria. So the idea of this project is to look at the stuff on Earth and to see, well, what are the biosignatures left behind by those microbes? And if you cut them open and put them on the beamline, you can find that not only in visible light can you see these filamentaceous structures from these microbes being formed, but you can then also track that with a number of different elements. Here, you've got calcium that can be shown in these ends of the filaments. And then gallium, which is important, can display the sheath that these microbes form at depth within these samples. And the other thing about gallium is it's not very mobile on Earth, on the surface of the Earth. So it stays around through geologic time, which is really important if we want to actually go back to this location, pick up this rock and bring it back and see if there's anything that once upon a time was growing in it. Also, here's a gratuitous image, a very pretty image that Gordon and Tom Jones allowed me to use. This is some mine tailings from Princess Creek in Tasmania. And here you can see mobility of different elements that are being moved around by the weathering of these tailings at different rates. So in this image, iron is in red, copper is in green, and zinc is in blue. So you can see that the copper and the zinc are being mobilized very, very differently. You've got a lot of copper being accumulated here in these areas. Zinc is sort of being slowly mobilized throughout the sample, even though normally it's a much more mobile element. Iron is seemingly unaffected. And it's gotten to the point where you've got this kind of structure here, which almost looks like a little bit of a snail, which I like. And when talking about trying to find those sort of single instances of very high intensity or high concentration of a particular element. This is a study that was looking at carbonatite melts from Inner Mongolia to try and see if they had platinum group elements nuggets in them, PGE nuggets in them. So we were able to scan very large areas very, very quickly. And this is one of the fastest scans that we do. We scan at 2 microns resolution, and we normally dwell for half a millisecond or less. So that means that we're scanning very, very quickly. We can cover these very large areas. And every time the beam goes across one of these platinum group element nuggets, it lights up like a Christmas tree. The Maya detector can see it very well, and then we can focus in on that particular element and or that particular nugget, and then get a much higher resolution map of that area. So here's an example of this, where you have these small little grains, these green grains occurring on the edge of this, calcium-rich, I think this is sulfide actually, within the carbonatite, showing that there are nuggets within this, and they are controlled by certain chemistry, which was looked at by this study as well. But it's not just the Maya. The Maya was really good for it to drive us towards mapping as fast as we do. But now, given that we already were doing the fast mapping, we've integrated that with our other detectors as well. So everything at XFM goes pretty quick. The vortex detector may not go as quick as the Maya detector. The Maya has the advantage of having lots and lots of elements and having high count rates that it can collect at. The vortex detector, you have to collect slightly slower, but it also has the advantage of having a much higher energy resolution. So where the Maya, you might miss some of these emissions when you have a lot of emissions from like rare earth elements, when you have a lot of transition metals in your sample, the vortex can normally separate those peaks out. So as an example here, this is a rare earth element map with uranium as well. And these two spectra are from this map, and they are showing the difference between the Maya at the bottom here and the vortex at the top. The vortex has a much lower total count rate, but each of these peaks is much, much cleaner, and so you can then use that to then map much better. And then we have historically had, before we got our DMM, we had this problem that we had this fall off in flux at higher energies. So if we went above about 20 kiloelectron volts above the molybdenum edge, we didn't really get a lot of flux from our optics, which meant that if we wanted to map something like cadmium in this sample, this is a plant that was grown in cadmium doped solution, we didn't really have the flux to be able to efficiently map at high resolution. This particular map was collected with 50 micron pixels, and there was about a whole second of dwell between each pixel here. And it's getting you can sort of see some differences in this sample. So the idea to fix this problem is get a whole new optic. So we did. We got what we call a dual multi-layer monochromator. So the difference here is that a DCM is using silicon crystals, and you diffract the beam through silicon crystals in a specific orientation of those crystals. You diffract the beam, you lose a lot of the beam, but you are able to set an energy very, very accurately with that. So that's where you get our very high accuracy energy resolution. The DMM is using a different technique where you have stacked layers of different substrates which allow the beam to diffract through at much lower angles. So that means you get much more light throughput, but you don't have the same energy resolution. It essentially means you get 10 or more times as much flux at different energies. In fact, at our high energies, we're getting 100 or 1,000 times as much flux as we're getting off our DCM. But it does mean that we can't do some of our other techniques like spectroscopy with this optic, which is a bit sad. But you can then map for your heavier elements. So here's a little bit of the install of the optic. Our great tech, Alan Easton, who did a lot of the work, is just hiding behind the optic there. Our optic hutches tend to be pretty full, so yeah, space is a bit tight. And here's us actually putting the lid on. The multi-layer is here. You can see the stripes of different layers on that particular optic as well. And we got first light on this back in 2024. So I've been using this for about 18 months and it's been going very well. And Olivier knows this optic quite well because she uses it for her studies on indium. So this is one of her maps that she happily provided me, where we can now access K edges of elements, which are much brighter than L edges and less confused and there's less overlap with different elements. But we can access these K edges all the way up to tin now, which means that gives us access to other critical metals like palladium, indium, silver. We can do cadmium studies for toxicity. And at the moment, it's only limited to our vortex detector. But again, soon, TM, we will have our germanium detector, which will mean that the efficiency of this collection is much, much higher again. So here's just a nice periodic table of all the elements we can reach. We have a low energy cutoff at silicon. Aluminium's kind of a bit gray, a lighter gray, because we can sort of see a little bit of distribution of aluminium, but not really anything quantitative. Everything from silicon above we can do quantitatively. And we can do XANES on anything here with which the DCM can access. So it's the vast majority of the periodic table, apart from some of this light stuff. So that's all well and good, but I'm here to talk about multimodal techniques and what the hell that means. So I'm going to talk about some correlated techniques that we can do at XFM. And the first one I'm going to talk about is spectroscopy. So just a bit of an introduction to spectroscopy. I said very early on when I was talking about X-ray fluorescence that there's a component of how X-rays are absorbed by atoms, which is controlled by the ionic charge and the bonding environment of that atom. And that's essentially being controlled by the density of the electron cloud and how bound those electrons are to the host atom or the host nucleus. In iron, this means that you get different emission spectra from iron 2 versus iron 3. In a lot of elements, this change might be a shift in, say, the white line, which is this big line here. And so you can then fingerprint different chemical species within a sample to try and understand what your iron or your gadolinium or your whatever you want to look at, how it is actually bound and moving around within your sample. Yep. So to do that, we do that here in 2 dimensions. Basically, what you're doing is you're collecting a map at a given energy. You can change the energy of the beam slightly and then collect it again. And then do that again, collect it again. If you do that enough times, do that 100 or so times with given spacing, you can build up maps like this where you can then extract what we call XANES spectra, which will tell you about the bonding environment within a sample. This is a bit of an older study now, but this was looking at the weathering of copper from tailings in Brazil and how that copper was being liberated from bornite and covellite and its interactions with iron when it entered into the precipitates and became a lot more mobile within those precipitates. I'll also include Jess Hamilton. This is one of her studies that was looking at carbon sequestration in tailings. I don't necessarily have the spectra from this particular study to show you, but much like some of the work you guys do up at SMI, looking at carbon sequestration in tailings, it's a very similar sort of thing. But here, Jess was specifically looking at how nickel and iron were moving differently within a sample and what they were bonded to and how nickel and iron were changing their oxidation state as they were going through these redox fronts that you can see within these samples here. More recently, we've had some people work on uranium XANES at XFM and looking at understanding hydrothermal rare earth element minerals, which can be contaminated by uranium. So normally the general consensus has been that within hydrothermal systems, uranium will deposit in phosphate minerals like monazite and rhabdophane as a reduced uranium form. But this study showed that, especially in rhabdophane and in a lot of monazites, it's actually a much more oxidized form. So if you have these oxidized fluids producing hydrothermal systems that have rare earth elements being deposited in things like phosphates or in rhabdophane or monazite, you can't just say, oh, it's an oxidized system, it's all happy, it's all well and good. We're able to mine this nice and easily. You need to actually take this into account because uranium contaminating rare earth elements is a bad thing. There's a lot of legislation around uranium, obviously, because it is a radioactive element. But there are some slight problems with collecting XANES, and those problems come from crystallography. So in certain minerals that are strongly oriented or strongly oriented, you can get polarization effects from the mineral. You can get crystallographic influences on your XANES spectrum, which means that the XANES peaks that you get out of your data can be shifted around. This means that you're not as accurate with when you study these if you don't account for this. So Michael Jones and Christoph Schrank have been working a lot on this particular problem, trying to understand how you can solve for this. And they're over at QUT. But this is where I have to introduce diffraction. So a lot of you probably understand diffraction pretty well, but the basics of this are crystal lattices are made up of planes of atoms that are stacked. There is this given distance between those planes in different orientations, different symmetries that can act as planes, and X-ray wavelengths approach the spacing, the distance spacing between those planes, so they can interfere with each other and diffract through a sample. And this is different for different minerals because there's different spacings and different orientations. So if at a given angle, you can get constructive or destructive interference between your incident X-rays as they pass through, as they diffract through your sample. You can also change the wavelength to get the same effect as well. So what does this mean? It means you can get really pretty spots and solve for a crystal structure if you really want. But in our context, we can use this as a measure of orientation of your grains. So here we can collect Bragg diffraction peaks with our Meyer detector in a backscatter orientation. These will, like here, show up as these very, very bright pixels with a lot of counts, as opposed to the surrounding fluorescence counts that we're collecting. And this will be in our elastic scatter maps. So this means that you can work out where they are in angular space around the detector, work out how far away they are so you can relate them loosely to different minerals, but then generate centers of mass and then build an orientation map from this data. And that means you can do some things like this. So this was a study where Christoph and Michael were looking at a gold deposit in chlorite-hosted gold deposit, where they were trying to understand how something like this big grain of gold here was relating to this sort of microcrystalline or micro nugget gold that was surrounding it. And there were some very interesting textures around the nugget where you had the nugget, you had a very low zone of gold here, and then you had this precipitate zone around it. And so to understand this, it was key to try and understand orientation because we were looking at a very strongly oriented mineral. And we wanted to understand if the iron chemistry was affecting the gold deposition. So they built up these maps here, solved for the orientation, and then we're able to take data from their XANES maps that essentially made it so they were looking at a pseudopowder. So they may not have been looking at, say, all the same orientation of crystal or something, that you want to average out the orientations to get the best data. So it's very much like you've crushed up the rock and then looked at it. But here we don't want to crush up the rock because it's on a thin section already, and that's useful for other things. So this is an effect that is evident with a lot of very strongly oriented minerals. and has different effects with different elements, depending on what their spectral characteristics are. Normally, traditionally, you would do this with an SEM and using EBSD, but we can do this sort of study over a large area in about 12 hours or so. An EBSD to collect the same amount of data would take 100 times as long, so it would cost you a lot more. It would also be a lot more sample prep. Also, we get co-located trace elements. We can do simultaneous XANES, and the advantage is we're probing the whole crystal depth. We're an X-ray probe, so the X-rays penetrate into the crystal a lot further than with an electron probe. So you're actually getting a representative analysis of your whole crystal rather than just of the surface. And then this brings me on to microdiffraction. I know I'm slightly running out of time here, but hopefully I'll get to the end. This brings us on to microdiffraction. So not only can you collect the backscattered diffraction to the Maya detector in its backscatter orientation, but you can also, if you don't have a backing on your sample and it's reasonably thin, so on the order of hundreds of microns, you can collect through diffraction. So this is photons that have been diffracted by the minerals within your sample, structures within your sample. We can bring our Eiger detector to a close distance from the sample and collect those photons that are being diffracted. So you can then collect a trace element map like I did here with a meteorite. You can try and highlight some areas of a mineral with a given chemistry that you're interested in. Here, I'm interested in some camosite. So this is iron-rich iron-nickel alloy. In our programs in GeoPixie, which is the program we use to process all of our maps, you can highlight all of those pixels and you can save all the addresses of these pixels. And then for this map, when we were collecting with the Eiger, we have a diffraction pattern for every pixel of this map as well. So you can then sum all these diffraction patterns together. And whilst each individual pixel may only have a few hundred, a few thousand diffracted photons in it, which you can't really solve for any structure on, you can sum them all together and get a lovely looking diffraction pattern that then can be pushed through to a 1D data reduction stream like Dioptas, and then you can push it into some peak identification software here, HiScore. So that gives you the advantage of not only being able to map for trace elements down to 2 micron resolution, but having a diffraction map per pixel. So having a diffraction map at the same resolution you've got your trace element geochemistry. So to put this into practice, again, this is from Christoph and Michael, who've been really good collaborators on this particular technique development. This was some myelinite, ultramyelinite shear transitions that they were looking at, trying to understand how slip was accommodated within mineral grains and how different minerals were being altered by the transition between myelinite and ultramyelinite. And also some other things like porosity changes and things that, if you want to know more, there's a couple of papers that have been put out about this. This was recently collected data as well. This was only collected at the end of last year. So first of all, we need to understand what are the minerals within our sample. And then we want to know how they're different as they transition across the boundary between ultramyelinite and myelinite. So here we're able to identify a few different minerals. I've just highlighted 2 here. And you can see that they've got very distinct diffraction patterns. A key thing would be then to go further with this data and identify what this biotite over here, how that was different to this biotite over here, obviously. There is some other peaks in here that haven't yet been fully extracted. But the key thing here is that this was a 2 micron map over a 20 millimeter by 10 millimeter area. So this map has about 200 million pixels in it. The great thing is every single one of these fluorescence pixels also has an associated diffraction pattern with it. So that's a lot of diffraction patterns you need to sort through whenever you want to get some data out, but you have that data now to be able to understand crystallographically what your sample is doing as well. And then this also brings us to an area of microdiffraction versus wax data, so wide angle X-ray scattering. So here we can talk about some amorphous phases as well. Back at the start, when I was talking about the high resolution mapping, I was talking about this project looking at hydrothermal silica deposits to possibly look at the Martian ones if we can ever go out and pick them up and bring them home. But this was looking at how in these stromatolitic textures that we see in a lot of these digitate-like structures, these finger-like structures in these hydrothermal systems, how the silica is being deposited. Is it being deposited as purely amorphous silica? Is it being deposited as some form of opal, opal A or opal CT, or is it eventually forming things like quartz? It's also useful then to map other minerals like halides or oxides or sulfides within the sample as well. And as we saw before, ultimately the aim of this project is to look at those biosignatures and see if the microbes are actually altering the silica structure as well. So what does this look like? Well, we can highlight 4 different areas within this sample where we have this stromatolitic texture with some slightly different chemistries, and then this sort of draping silica around these digitate textures to see if there's a change in the resulting scattering of the photons. And hey presto, they kind of look mostly the same. Don't worry about these 2 big peaks here. Those are just from beryllium windows on the Maya detector. They will appear in every diffraction pattern, unfortunately, because you're passing the beam through the Maya detector to get the fluorescence response. And I didn't have time to extract them out of this particular pattern. But you can see in 1 and 2 and 3, there's varying degrees of some of these other shoulder peaks. But this main scattering peak here is the one we're interested in to try and understand the crystallinity of silica. As this gets sharper and sharper and sharper, you're getting more and more and more order within the silica that is being deposited within these stromatolitic textures. You can also see some small little peaks on the side. This is mostly halite. But then once you get to this draping texture here, everything sort of changes. You get far less structure from the silica and much more structure from some other minerals that are within that as well. And now I'm going to talk a little bit about ptychography. So ptychography is a computed technique to take a STXM, so scanning transmission X-ray microscopy image, and build a super resolution map on top of it. So this is a diffraction technique. It's looking at the scattering of the beam in very, very short angles at very long camera lengths to try and build up very high resolution maps. This is just showing you some of that super resolution that we can produce. This is a Siemens star. Don't worry too much about it because I've got a rock to show you here. This is doing some of this mapping on, again, from Christoph and Michael, on some of these structurally important calcite-hosted fault zones from the Alps in Switzerland. So this was collected on a 30-micron freestanding thin section. It's a bit hard to prepare for some of the ptychography, but the advantage of this is you can get down to very, very high phase contrast pixels with this particular technique. Get down to 25 or lower nanometer pixels to get structural information on your sample, phase contrast information on your sample that you can then also relate your chemistry to as well. So a bit about access. I felt like this was the best time to give this talk because next week our next round opens. So hopefully I might have sparked some interest in putting in a proposal for us. March 25th, our next access round opens for merit proposals. So merit proposals are essentially like you're applying for a grant to do work at the synchrotron. You apply for a certain number of days of beam or shifts of beam, really days of beam for XFM. You write your science case, you write why you need synchrotron radiation for your science case. You talk to myself, David, or Daryl about your experiment and get some advice from us about how to best prepare your science case as well. And then that gets reviewed by external reviewers. And then we have a committee that goes through all the proposals and ranks them. And then people get awarded based on the feasibility of the study and the impact of that study. So that's all through the merit proposal rounds where it's a bit more competitive. There's also a commercial way to get beam time. Basically, if you pay us money, we will give you beam time. This has the advantage of all of your results will be confidential. You own the IP. You can normally get access much faster to the synchrotron as well. It's normally within once the negotiations for contracts and stuff are done, you can normally be on site within a few weeks of signing everything up. And there's different levels of service we can provide, whether you want us there all the time to help you with all of your data collection and processing and producing a report, or whether you think you can produce all that yourself and just come to collect the data. If you do want to put in a proposal, please go to our portal once it's the 25th and start a proposal. Please talk to us about it as well, because we'll have some advice and stuff for you. And there are a bunch of advantages. Basically, Beam is available 24 hours a day, 5 to 6 days a week to do your experiments. Experiments will run, some beamlines run for a few hours. We don't, we tend to run for 1 day up to 6 days of beam time. So you've got a lot of time there to collect good maps. Some beamlines can run thousands of samples. We can't. We would normally say tens of samples. Bring tens of samples when you come along and you'll be able to get really great amounts of data. But we do produce a lot of data. Hundreds of thousands of data sets, 10 terabytes of data is not uncommon for an XFM experiment. But we'll give you the training and the support to go through and reduce that data down into a format that is usable by you. There's 24 hours of support, 24-hour support available from our operators. But we also have a whole structure, a whole compute infrastructure to allow you to process your data into a format that is best for you. We host that. We host your raw data as well for a number of years so that you're able to access it and use it as you need to. Also, the best benefit is that there is unlimited coffee to keep you awake during the late nights of lots of data collection. I think that's about it. Yes, it is. Thank you very much for listening to my long-winded talk. If you have any questions, by all means, please ask away. Or you can get in touch with me via the 2 emails that are here. The AS-XFM email will go to the whole team. So it may not just be me answering. I am the only geologist on the team, but that doesn't mean that David and Daryl don't know a lot about this sort of stuff as well. And I'd be interested to hear what people think this particular map is of. Thank you very much.
And you? Here is, so I think the Rossi Blaming raised his hand. Okay. Yeah, I think I changed. Can you hear me?
I can see someone with a raised hand.
Can you hear us, Andrew?
I can hear you, yeah.
Okay. So we think Rosie has a question. Rosie?
Yeah.
Hi, sorry.
Hi.
Problems.
I can hear you now.
Think I raised my hand by accident.
Oh, no.
But, let me see if I have a question. Yeah, I guess I'm interested in analysing some mine waste samples. And I was just talking to Olivia about this yesterday and looking at how critical metals like cobalt kind of go between primary phases like chalcopyrite and pyrite and into secondary phases. So is that something that you can look at with XFM, like do maps of jarosite or kind of secondary salt phases and that kind of thing?
Yes, so we can. There is one caveat I will give to that, which is that mapping cobalt can be a bit tricky with all energy resolving techniques. So we're essentially an energy dispersive technique. And unfortunately, when you have weight percent of iron and parts per million, hundreds of parts per million even of cobalt, the iron fluorescence will dominate, and there's a strong overlap between the emission of the K beta emission of iron and the K alpha emission of cobalt. They sort of sit very, very close together in energy space. We do have some methods to try and get around that. There's a couple of different techniques you can do. One is that you can do multi-energy mapping. So you can map at two different energies, one above the cobalt edge and one below the cobalt edge. And then you should be able to see that sort of the change in those maps and be able to solve for cobalt. There is some work going on by our nanoprobe team to try and improve energy resolution from these sorts of detectors. And then there's also a technique called HERFT, high energy resolution from diffraction is the acronym. But basically it's essentially a synchrotron-based WDS technique. So that's much like in a microprobe where you have a WDS detector, you can select specific wavelengths of light that you want and reject everything else and just hunt for that sort of thing. That's available at XAS at the moment. So that's a bulk technique, unfortunately. I would suggest if you want to put in a proposal about trying to map cobalt in iron-rich samples, have a chat with myself. And I'll also probably loop in Jess Hamilton as well, who's been working with me to try and improve our detection there.
Yeah, great. Thank you. I'll get in touch with you then. Thanks.
No problem. Thank you.
Do we have more questions from audience or in the chat? Let me see. Here we have a question. Hi. One second. Any advice on how to prepare samples comprising thin section of rocks for XFM? How well polished do they have to be? And does coating affect the quality of the maps?
Yeah, great question. This is a question we often get. Your polish for an XFM thin section doesn't need to be as high as it needs to be for SEM. So if you're already preparing your samples for SEM, then you're more polished than you would ever need to be for XFM. In fact, we can take samples that are mostly just straight off a rock saw. There are some sort of caveats with that. We will have you'll see a bit of the texture of the saw. But yeah, you don't have to be extremely well polished to run something at XFM. Coatings, normally, if they're metal coatings, they will have a big effect. We will see the metal fluorescence, even if it's very, very thin. Carbon coating, you don't have to worry about. We are not sensitive to carbon. We cannot see carbon fluorescence. It may scatter the beam a little bit more, but that doesn't really matter because it's very, very thin coating anyway. The one big thing that does affect your ability to run, to get good maps out of XFM is the types of slides you're preparing your samples onto. So in that case, you want to have slides that are very, very clean. We recommend looking at things like electrically fused quartz. There's a set of slides from SPI, which are electrically fused quartz that we would recommend. We've had very good experiences with. And the reason for this is most optical glasses have contaminating elements, or what we call contaminating elements. They're essentially elements that are there to improve optical clarity. So they might be things like arsenic or cerium or rubidium, iron sometimes. And if you're interested in any elements that are within that energy range, you're going to get a strong response from the slide. Because our X-ray beam will penetrate all the way through your sample and into that glass, and you will get fluorescence back from it. So you need to make sure that your glass is very, very clean so that you can get the best maps possible.
Thank you, Andrew. I have a question. When you mentioned that it's possible to separate the elastic signal in the Maya, that is also possible using the DMM? It was just an example, or it's possible in both? Okay.
Yeah, we can do it with both.
Okay.
Yeah.
I think we don't have more questions. People also wrote, thanks, Andrew, great presentation. So thank you very much, Andrew. It was great to having you.
No problem. I will just mention,
yes.
Tom has put in the chat, Tom
Yes.
Jones has put in the chat that if you want help with any sample prep, get in touch with him.
Yeah, we have help here.
Fantastic.
So yeah, if no more question, yeah, please, thank you to Andrew and for your time and all this knowledge you share with us today.
No problem. Hopefully not too many people fell asleep when I mentioned maths.
I'm sorry? Yeah, the critter, yeah.
Oh yeah. So this is a lobster larvae. So this is one of those sort of very early life stages of lobsters. They float around just in the ocean. They're about 200 to 400 microns thick. And then the tasty bit of the lobster is going to be this last little bit here, which is the tail, which doesn't develop until the very final life stage. Here we have copper in its gills. So they use copper in their blood to transport oxygen around. And then there's potassium in the shell. And then I think this is bromine in the muscle fibers and in the eyes. So yeah, lobster larvae.
Thank you, Andrew. That was amazing.
No problem.
Thank you so much.
Thank you, everyone.
Bye-bye. Thank you.